Welcome to the AP Chem 2022 FRQ video series. Today we'll be solving question 3 of the 2022 AP Chem free response questions released by the College Board. Whenever a question pops up on the screen, please pause the video and read it to yourself. So for part A, we need to give the ground state electron configuration of aluminum, for which you would look at the periodic table, and then you just go subshell by subshell, and then we end up with 1s2, 2s2, 2p6, 3s2, and 3p1. For the next question, we're talking about why the radius of aluminum is larger than its +3 cation. So considering that the cation has lost electrons, the aluminum atom has more electrons in it, and that increases the electron shielding, which in turn decreases the attraction between the protons in the nucleus and the electrons for the aluminum atom. And by Coulomb's law, that means the radius, as in the distance, is going to be larger for aluminum. Part C now asks about writing a procedure to prepare 200 milliliters of aqueous solution of silver nitrate with the following equipment. First, we're going to use the scoop to scoop out the weighed silver nitrate and then place it in the beaker. So this is taking care of the solute. Next, we're going to use a volumetric flask to take care of the solvent. So we're measuring 200 milliliters of water. And then remember, for these flasks, we're going to be filling it up to the calibration line. So we have to say that as well. Now what we're going to do is we're going to combine solute and solvent, pour the contents of the volumetric flask into the beaker that we use in step 2. Then we're going to stir until dissolved. So now part D gives a reaction with the solution that we made in the previous part, and now adds a sample of aluminum to it in order to have the reaction. And in part D, they have this particular diagram, and then they want to know basically what the product side of the reaction is going to look like given this many particles in the reactants. So the first thing that we need to do is observe that we have aluminum solid, which gets reacted into silver. So here we can see that we start out with 4 aluminum and then we end up with only 2, which tells us that 2 of the aluminum must have reacted. So when it reacts, we need to then again consult this ratio. So for every 1 atom of aluminum solid, we get 3 atoms of silver. Okay, so now here we're saying that 2 of these have reacted. So now this is getting doubled times 2. So now we have 2. Well, then we also need to double this side of the ratio. So then that means that we're going to have 6 silver atoms for the 2 aluminum that reacted. And when we draw this in our particulate representation, we have to remember to make the silver atoms bigger, and also because it is a solid, the relative spacing also does need to look like a solid, so it needs to be packed together. We need to look at the silver ions. So we know 6 silver ions have reacted, and since we started out with 8 on the reactant side, that tells me 2 of them are left over. And now, of course, we have 2 aluminum left over that, of course, did not react, to form the silver solid. So those are going to also be ions swimming in solution and have to be smaller than the Ag. So for part E, we have these standard reduction potentials, half reactions in a table. This is an electrochemistry question. This is a galvanic cell. This is the cathode. This one is going to be the anode. All right, now we need to calculate the value of E. So for the galvanic cell, remember we do have the formula. So that's going to be E cell equals E of the cathode minus E of the anode. All right, so what we need to do here is we have these E values, and remember for a galvanic cell it always has to be positive, so E cell has to be positive. So our thought is going to be, all right, how can we like arrange these values to give us a positive result? So one thing we can do is we can say 0.8 minus negative 1.66, or we can also say negative 1.66 minus 0.8. So these are our two outcomes, and then this is what's going to give us a positive answer. So now for part F, it asks, would the standard free energy change be positive, negative, or zero? Well, when it comes to this point, we need to think of this equation over here. So this is what you should be thinking of. And then we know that N and F are both always going to be positive. So our value here, our value of G, is going to depend on our value of E. So really, if you look at it, it's negative E. So our value of G is always going to be the sign opposite of E. And our E was positive in the previous part. So that means because E is positive, G is negative. This can be seen in the equation. Because N and F are always positive, the sign of G is always opposite from E, unless both are zero. So now, when we look at part G, it says once the reaction appears to stop progressing, would the change in free energy now be positive, negative, or zero? So one thing that we can think about is when it stops progressing, this is indicating a state of equilibrium. So that's what we need to take away from there. And then at equilibrium, so this is just something that you need to know, at equilibrium, E cell is going to be equal to 0. And then this is for a galvanic cell, obviously. So when we go back to our equation over here, this is going to be 0, which then also makes G 0. And that's all for this video. Thank you for watching and good luck studying!